Welcome back to this second part of the lecture on collision detection and reaction for robot manipulators. We have seen that there are several ways in which we can use the information coming from the momentum-based residual that detect and isolate collision in order to react to a collision once this has been recognized. The most natural reaction is called reflex reaction. But in fact, we have a possibility of doing several types of decision based on what we are doing. So in this slide, I'm showing now the possibilities that there are, looking also at the amplitude of the residual, because we noticed from the experiments that the amplitude of residual is more or less proportional to the severity level of a collision. So in these schemes, we see that there are multiple options for reaction. In particular, when you want to preserve part of the original task. So here you see that once the detection has been recognized, we can stop definitely, and this is one possibility, in particular if you're only able to do detection and not isolation. Or you can have a reflex reaction. The reflex reaction does not take into account at all what the robot was doing originally. So there are other methods that try to preserve as much as possible of the original task. If you were doing a Cartesian path, but in principle also a joint path, and with a given timing law, you may decide to preserve the path and rescale time by stopping and possibly reversing because of the presence of a collision or an obstruction. In the same way, you can, if you have a Cartesian trajectory, so you want to keep now both the path and the timing law, so the full trajectory, and your robot is redundant, because otherwise this option cannot be pursued, then you may try to preserve the whole task until the collision is passed, until the contact force that is preventing you to do what the robot was doing is removed. In effect, if those strategy cannot be pursued because of the large persisting amplitude of the residual, in case of the time scaling, you abandon completely the task, so you you activate a reflex reaction. In the second case, instead, you may try to start a partial relaxation of the task. For instance, you can abandon the specification on orientation and preserve only the position. If everything goes well, so that the collision is surpassed, then you can reprise the original task, maybe compensating with what you have lost. In case the task relaxation is not enough, then again you return to the basic reflex reaction and eventually stop. So this is a kind of portfolio of possible reaction strategy. Of course, you may combine them, you may think of something else, which depends, however, context dependent, while this type of possible reaction strategies are quite general. So let's see the time scaling and the use of redundancy with possible task relaxation approaches. Here you see a setup of the experiment with former master student, now full professor Sami Ad-Din. You see that the motion prescribed was hitting the trunk of the body of Sami, and these are snapshots, and that shows all possible situations that can happen. So the robot moves, touch the body. The trajectory is being scaled, possibly stopped, and possibly also reversed if the user is pushing against. When the collision is detected, however, so then the residual is too large, then there is a reaction and the robot goes, for instance, in torque control with gravity compensation, which is the floating mode with zero gravity. Okay. The underlying assumption is that the robot is position controlled so that it should follow a given geometric path with a given timing law. So the timing law is what can change, slowing down, stopping, even reversing the motion along the same path, and then restart. So here in this video you will see the various possibilities, and please notice the interaction that will occur at the contact. So when the user is in fact pushing more on the robot, making the residual grow accordingly. So in this case, just to stop, return, and the trajectory is reprised as soon as possible. But if you push too hard, then you have this type of reflex reaction. Again, trajectory scale stops, but if it receives a strong push, then the reflex action takes the lead and the task is fully abandoned. Okay, so this is rather clear. This trajectory was a simple trajectory, but of course you can make things more complex. You may also abandon the trajectory for a while and then recover the same trajectory again. In particular, what about the use of kinematic redundancy? We have seen already, we have treated the multiple use of redundancy, but this is another one, an additional one that we developed. So, under the umbrella of preserving as much as possible, if it's possible, in fact, the execution of a planned Cartesian trajectory in the presence of extra degrees of freedom, we would like the robot to behave more or less like follows. So at the given instant tk, and this tk is the instant of collision detection, we were tracing the Cartesian trajectory, and a collision occurs along the body represented by the red arrow fk. So we would like to continue the motion in the Cartesian space also for instant of time which follows the collision detection instant, provided that we are able to accommodate the internal configuration of the robot so that either we remove the collision or at least we milden the effect of this collision on the residual. So even here it's a matter of defining a number of thresholds. If this is not possible, we may still preserve position but maybe abandon the orientation specification of the Cartesian trajectory. And if everything fails, then abandon completely the original task. Now, how do we accommodate a reaction to a collision while preserving the original task? Well, this is a dynamic version of using kinematic redundancy. So let's formulate the task in general setting. The task will be defined by some set of coordinate x, m dimensional, and we have n degrees of freedom available, so we have redundancy. So we write the Jacobian of the task, so the relation between the velocity in the joint space and in the task space. The task space may be the Cartesian space or whatever. And then also the acceleration level, because we need to include now dynamics. So we have x double dot, which is jq double dot plus g dot q dot. Now written in the reverse order is the same. Now you consider, for generality, all possible generalized inverse of the task Jacobian. And we call a generic generalized inverse with a g. This may be the pseudo-inverse, a weighted pseudo-inverse. Remember that this definition is the minimum request for having the possibility of executing the tasks which are feasible, so that which lies in the range space of J. So G is a generic generalized inverse. Now, if you want to solve the acceleration relation in terms of q double dot and write the all possible acceleration that realize the same desired x double dot in a given state q dot, this is the form that you get. You get a term which is related only, for instance, if G is the pseudo-inverse, the first term would be the minimum norm solution in terms of norm of the acceleration, and then you have an additional acceleration projected in the null space. You are used to see this equation probably with the pseudo-inverse in place of G, but in fact this applies to any generalized inverse. You may not have the orthogonality between the two terms like you do instead when you're using the pseudo-inverse as generalized inverse, but this stays in place. Now this acceleration has as a parameter of degree of freedom the null space acceleration q double dot 0. Now we plug in this into the dynamic model and we transform, since we know that there's a one-to-one correspondence between joint acceleration and torques, like we put this acceleration into the dynamic model and we compute the torque, we will transform also the acceleration q double dot of 0 into the unique corresponding torque tau 0. So that we have in the null space of a dynamic problem a torque that can be used for reacting. So the task acceleration is given by x double dot, and these two terms are one independent of the other. So the first term realizes the desired task acceleration, while with the arbitrary joint acceleration we don't perturb what we are doing at the task space. And this is true for any generalized inverse. Now, in the model for compactness of formula, we group the colorless and centrifugal and the gravity term into a single vector n of q dot, and then we substitute the previous acceleration into the dynamic model, and we rewrite the acceleration q double dot 0 in terms of the equivalent torque tau 0. And we end up with this formula. Now, in this formula, the acceleration of the task, x double dot, follows the desired profile, and probably because of robustness and for recovering any error that may have been arised, we closed also a PD control in the task space in terms of the error, which is x desired minus the current x. The full matrix that, the long matrix that pre-multiply tau 0 is in fact a projection matrix in the dynamic null space of J. As you can see, the inertia matrix appears twice, once direct and once with the inverse. Indeed, the identity remains the same if you execute the product, but the second term will contain both the inverse, the mass matrix, and the inverse of the mass matrix. While tau 0 will be the joint torque left free for reaction that we were looking for. So we will just plug in an n-dimensional torque tau 0. For instance, in the reflex strategy, we will choose tau 0 equal kr times the residual, and this will not affect the task as long as the residual is kept limited or even reduced, because we are mildering the effect of the contact by the choice of tau 0. If this is not the case, we should abandon part of the original x double dot, for instance the orientation part, achieve the same type of control law, and again, if this works, then we may even reprise orientation control together with position control, or we need to abandon everything. So the outcome of this very quick analysis is that when you choose any generalized inverse, then the joint torque tau may have these two contributions. The one for performing accurately task acceleration control, the other that does not affect the original task, but is used, for instance, for reacting to collision. Now, among the possible choices of the matrix G, it is suggested to use the so-called dynamically consistent generalized inverse of J, which is nothing else than an inertia-weighted pseudo-inverse. And the way in which this methodology is pursued can be obtained by following really a dual derivation of what we have done at the level of velocities, so finding the minimum norm solution and then finding the null space term and so on and so on. But now we work on force transformation. In fact, remember that we have contact force, generalized contact force at the Cartesian level somewhere on the robot structure, and then we work in the joint space with torques. So the mapping is in general tau equal J transpose F. Now the J is in fact the J of the original task, so for instance an effector motion, so it's something that we know, and F is some forces that will be a control force. Now we can decompose any joint torque in one term coming from a force which is defined at the Cartesian level, and this is J transpose times F, plus an extra torque which has this form of with a projector where H is a generalized inverse of J transpose. Okay, so that tau 0 is the additional torque in the joint space that cannot be generated by J transpose times F. In fact, if you replace J transpose F in place of tau 0, so that you assume that tau 0 can come from a Cartesian force, then the second term vanishes, because H is a generalized inverse of J transpose, so J transpose H, J transpose will be equal to J transpose, and then subtract with the first term the identity times J transpose. So this means that the torque in the joint space can be decomposed in this nice way, much in the same way as the joint velocity in the joint space can be decomposed in those that realize a Cartesian velocity with some property, for instance minimum norm, and another self-motion type. So these are kind of self-torque decomposition. Okay. Now the convenient choice for H is in fact the one in which you see a transpose of the inertia weighted pseudo inverse. In fact, since we are working in a dual way, our G, which is defined kinematically, will be just the transpose of this pseudo inverse, and in fact it will be the conventional weighted pseudo inverse of the original Jacobian, where the weighting is given by the inertia matrix itself. If you replace this particular solution into the general form, you have the dynamically consistent solution, which has the characteristic of having a leading J transpose in front of the main term. So this is what we have simulated in the first place to understand if we could organize a level of threshold in order to preserve as much as possible the original Cartesian task. So here I have a simulation in which the KUKA lightweight robot has been simulated in a Simulink environment, and then the visualization here was made in VRML. The end effector should follow a straight path in position and constant orientation, while it encounters a spherical obstacle placed more or less at the level of the elbow. Now we will if you move around the spherical obstacle, you may do the task completely. If the spherical obstacle is getting closer to the elbow, then you may hit and try not to relax the task, and so preserving both the linear path and the constant orientation, which is pointing downward, but then accommodating the force coming from the collision, namely with a reflex strategy projected in the dynamical null space that we have seen, so that you try to avoid the continuation of this collision. If this is not possible, then you try to abandon the orientation, and if even relaxing the task in this case you are not able to reduce below a certain threshold the residual, which means that you're forcing motion against the colliding object, then the task is fully abandoned, because we give at the end priority to safety. Here there's no human involved, but in a general sense, safety means you don't want to interact too much heavily with the environment, so have large contact forces. So in this video you will see 3 cases. First, no task relaxation, and you will see how the reconfiguration is being performed in the joint space. Then relaxing the orientation because the residual are not being able to be reduced. This occurs by bringing closer the position of the spherical obstacle. And finally, a situation where you abort completely or you abandon completely the task. So no task relaxation, you see that there's a hitting, but you have seen that how the robot has accommodated its configuration. This is a different view of the same task. Now, by relaxing the task, you see that the orientation has been abandoned in order to preserve the original task. And finally, a situation of stop. And here you see the 3 levels of value of the residual that are being correspond to the 3 previous behavior. The first case, below a threshold, we can do the task completely and we react to the collision. The second, we react to the collision, but we can preserve only one part of the task. And finally, we have to stop and abandon completely the task. Now, many years later, after this simulation of 2008, we performed also experiment with our lightweight arm in the lab. So here there are more things involved. We use, by the way, an admittance controller here in order to move the arm. So the method is slightly different from what I presented, but the results, I think, are very clear. So here there are 3 situations. The idle situation is when, in green, when the robot is doing its task as planned. The relaxation is abandoning in part the task, and abort or abandon is when the task is completely abandoned. The difference is that the human is there now interacting with the robot, and when the robot needs to abandon its task, then it follows the human under the action of an admittance control. So the force that the human is exerting on the robot is being detected and estimated by the residual at the joint, and this residual are treated like torques, and the torques produce some velocity. In this sense, this is an admittance controller. Let's see the video and understand what's going on. So here the original task is executing this hexagon. Now if you're pushing, the robot is in the relaxed state, so it's releasing orientation but then recovering everything. Idle state, and now abort. You see that the robot has abandoned completely the task, but then it recovers and restarts the task from where it was left. Again, contact on link 3, the robot abandons the task completely, and returns then where it was abandoned. And there's also an estimation of the contact force. We will see this method in detail, how to estimate the contact force similarly. This is a relaxed state, so the position is kept until possible, and then the abort state. And the contact may occur at any link. You see that there's also a kinect overlooking the scene. Here you see a typical case in which the orientation is abandoned but the position is kept, so the relaxed state until this position where the robot is not able to follow the path. And so it abandons it while recovering as soon as the residual has come back to zero. Okay. In this video there were more because there was an explicit estimation of the contact force that is used for collaboration, and this will be the topic of our next lecture at the end of this one. Okay, so indeed there are other possibilities that can be explored. In particular, it's very interesting the possibility of distinguish intentional interaction, which may be associated to an obvious contact between the human and the robot, for instance shaking hands here, from unexpected collision. The intentional interaction should be treated in a way that is collaborative, okay? While unexpected collision, we should react completely, like we have done so far. Now, if you include in the robot also joint or sensor, and if the intentional interaction occurs at the level of end effector, then the situation is easier. In fact, you can include the measurement from the force or sensor in your model, so J transpose times the measured forces, and if you put them inside the residual, then of course whatever force is being measured at that level is treated as the desired one, a collision. So you can distinguish it quite easily if you know that the intentional interaction occurs at the end effector level and if you have a force or sensor. We will see more of that about a collaborative task in the last lecture. But now I would like to conclude this part by mentioning another work that we have performed in our lab on the KR5 robot, which is an industrial one with closed control architecture, where we try to do something similar to collision detection and possibly reaction and collaborative behavior, if we recognize that the contact is intentional, even without having at disposition a dynamic model, the accessibility to torque or current as commands, and the fact that our program should be interfaced to the low-level control law of the robot by just giving reference command QR dot here externally and working with a very slow interface that provides data every 12 milliseconds. As you remember, when we ran the experiment on collision detection on the DLR-ARM lightweight 3, we had a sampling time of 1 millisecond. So here we are at least 12 milliseconds slower. And this is let's say, the poor man version of what we have tried to develop on the research robots. The system provides as output from available to the user, the joint position as measured by the incremental encoder, and also the motor currents. You can see on the right hand side the typical profile of the motor currents of the first three joints. In fact, in our experiment we moved only the first three joints and kept the last three joints, so the spherical wrist, as fixed. There's a further complication in this case because in fact this data coming from the robot sensor interface are only absolute values of the motor current. In fact, as you can maybe recognize from the profile, you always have positive current. We made some experiment in which we rotate one joint in one direction and then in the other direction, and the current was still always positive, which is counterintuitive. So the reason for this further difficulty, which creates us a lot of troubles in fact, is because probably this current is coming from a PW modulator which has only duty cycles which are positive. So in fact the intention of KUKA was providing this information on the motor current only to monitor some fault, and so only the intensity of this current matter and not its sign, while for doing some elaboration, for instance for doing a model, dynamic model identification, we should be able to access and measure correctly the currents, the motor currents. So in this case, the only thing that we can do is to change the reference Q dot R. So if we set QR dot to 0, the robot will not move, no matter if we are pushing it or not. Okay? So we are trying now to make, through the definition of QR dot, a certain reaction. And in addition, since we don't have a model and we don't have the torque, we don't have a joint torque sensor, we don't have a force torque sensor, we don't have any other exteroceptive sensor, the only information that we can process is on the motor current and on the joint position. So, nonetheless, we were able to do collision detection only. In fact, you will see that when we collide, the motor current will change, but there is no one-to-one relationship between which motor current will change and which link you have collided with. So only detection is possible, not isolation. So the only reaction that we were confident to implement was stopping. Okay. So here on the right hand side you see the current profile for joint 1, 2, and 3. You see in red some trajectory dependent threshold. So when we exceed this threshold, then at least one of this signal exceeds this threshold, then we recognize a detection and the robot will stop. Now you will see the parts of these plots highlighted in correspondence to when in the video the user is colliding with the end effector, with the robot. The robot makes a periodic motion just to make it move, and there is a high pass filtering analysis of this motor current. So we are really doing a detection which is not model based but signal based, as opposed to what we have seen so far for collision and also for actuator fault detection and isolation. So here the video, the robot is making a periodic motion. Remember, only the first three joints are moving, so the wrist joint, the three wrist joints are kept frozen. So while doing this task, now you see that joint 2 and joint 3 current has exceeded their threshold. Again, joint 1 exceeded, so the robot stopped. And you see that the collisions are quite not too dangerous. Again, the robot is not moving really at full speed, but even small collisions are being detected in this way. So, for instance, this last collision occurred near to the end effector, but only joint 1 current exceeded its threshold. So it has nothing to do with where the contact occurred, and of course this is really a system with a minimum amount of information available of measurement. Still, we decided to go farther. First of all, the trajectory dependence of the threshold is important because since we are only working with signals and no model of their generation, we needed at least to have low threshold when we were moving slow and higher threshold when we were moving at faster speed. So this is one reason for that. In fact, the threshold has a strange combination of the desired current, desired velocity and acceleration. Still, the idea of filtering the current comes from an observation. Usually collisions are hard collisions. So they generate impulsive or impulsive-like peaks, like you can see from this profile. So the high-pass filtering forget whatever happens at low frequency and is being excited by this collision. On the other hand, if you do a low-pass filtering and you do it on the same variable, you can recognize soft contacts, those that will not excite the high-pass filter, but still excite the low-pass filter. So you can imagine to distinguish accidental collisions, which are hard, to intentional contact that are soft. And once you recognize an intentional contact, you may switch modality, so reconfigure your controller and start to collaborate. Remember that the controller still remains for us a kinematic controller because we can only specify some reference velocity, q dot r, outside. Okay? So here now in this second experiment, you see on the right hand side the high pass filter motor currents and the low pass filter, which are even more with threshold, which are even more dependent than from the trajectory being executed. And the first situation will be a collision detection, so stop a couple of times, and then there will be a soft contact. So this is a hard contact. In fact, you see that only the high-pass filter version of current exceeds their limits, and now a soft stop, and you see that you have the low-pass filters that generated the signals, and so the robot stops, and starts being ready for collaboration. Now in this collaboration there's a manual guidance, so the robot will follow the push of the user, whatever direction. Remember that this modality, the robot is working, it's its regular modality, so it's not a special mode. We are changing reference at the joint level, recognizing in which direction, I say, the robot is being pushed by looking at the small increment of the encoders and then commanding a velocity in that direction. So we are kind of cheating the controller and also the users, in the sense that what you see apparently seems a torque command by this kinematic control. And there are more ways in which you can achieve collaboration once you have detected an intentional contact. For instance, in this first of the two videos in this slide, there will be not really a manual guidance, but just a reaction by a small force. We will command a large velocity reaction and then stop. So this is pushing and pulling the robot in this way. So again, you stop it in a soft mode so that the robot understands that from now on it should collaborate, and then we program the pushing pulling modality. So with just a tiny force, a finger, the robot will be pushed away or pulled in the other direction. Now this requires some programming, of course, but the behavior is quite natural. And if you remember now the video that we have seen with the robot interacting with the environment, for instance the compliant control, where we were able to, you can apply also momentum like this. Okay, if you remember the compliant control, that was implemented, and I have shown a video from the laboratory of the University of Naples, in which you can realize compliant-like behavior, in the sense that without using the force sensor, the robot is reacting in a spring-like fashion. But in that case, we were able to, and they were able to impose current, so torques at the motors, and let them behave in this proportional way. Here we don't even know what is the low-level controller. So the only thing that we can do is modify the external velocity reference. Still, we can achieve compliant-like behavior in this fancy way. So again, the robot will be stopped in a soft modality. Okay, you see that all the and you see that the motion is like having the reference position as 0 and then reacting like a spring in the various directions. But this would generate a torque, but we are not able to impose this torque, so we have to mimic it by a special designed command at the joint velocity level. If you're interested, you can consult, of course, the original paper, which was a paper at the International Conference of Robotics and Automation of IEEE, ICRA, in 2013. And with this, here I'm reporting a number of papers starting from 2005, and then the collaboration with the German group, and then other works performed locally. This last result was the paper by Milad Geravand and Fabrizio Flacco and myself, 2013, and then this concludes this lecture. Thank you for listening.